Yeah, with my presentation.
Yes, I am right now. All righty. All righty, we are back now on YouTube. Welcome back, everyone. We had a lot going here in the few minutes. Just a note on this presentation, the live demonstration part will not be on the stream. We just simply do not have the capability to do it. So one of the advantages of being in person is you don't miss a thing. So make plans to come next year if you are just watching it on YouTube or on the Zoom stream today. All right, we're going to go ahead and get started now with our third presentation for the morning. The main track, we have an introduction to antenna modeling. And at this time, we're going to switch the screen over here to this, and hopefully it will switch okay and bring up Dave's presentation. And I'll set this up for him so that way he can go ahead and roll right into it. We'll segue into that, and hopefully it will give us the controls back. And let's see here. I'm trying to get that to do it. It can be a little hokey sometimes. It can definitely be a little hokey sometimes. Oh, I didn't share. There's what I didn't do. Okay, we're screen sharing now. Okay, there we go. Okay, so now you can see it on the screen here. We apologize for that. Don't do this often enough. So I'm going to turn this over to Dave, let him do his presentation, and there we are, and it is all yours.
Okay, thank you, Daryl. I left off this. I'm Dave Birnbaum, K2LYV, the original and only holder of that call from October of 1953, which kind of dates me. I've been an extra for a long time, and one of the decisions I sometimes regret is back about 1976 when the FCC first allowed vanity calls. One of the options, the only people who get a vanity call were extras. And those are the days where extra meant a devilish theory test plus 20 words a minute of code. And so I said, gee, I could have my choice of 1x2 calls. And a buddy of mine, also a K2, talked about, we said, you know, the thing about K2s is the only time they were issued was in the 50s. So it kind of it tells people where you are from. Sometimes I wish I had thought it through differently. But anyway, I've been doing this for a long time. And one of the things that I like to do a lot of more theoretical. I have a background in engineering. And so I like to do some things that are more theory or if you like, computer generated, then I also build stuff, but this is a different side of it. And one of the things I do is I spend a lot of time trying to figure out in my limited antenna space, how I can build antennas that will fit in the space, not annoy the HOA, and still allow me to get out in some fashion. So I've been modeling things like putting up antennas in my attic or running a loop around the garage and things like that. And so to do that, rather than spend a lot of time crawling around in my attic or garage, I figured let the computer model the antenna. So I'm going to talk a little bit about what that means and how you can do it yourself and why you might want to do it. So, here we go. So first of all, it's a lot easier to model the antenna on the computer than it is to go climbing up trees and stringing wire. And then on top of that, after you strung it up, now you have to figure out how do I trim it to work. The computer will let you do all that to start with. It will let you look at an antenna you already have and see things like what is the SWR like? What happens if I go off frequency? What does the pattern of the antenna look like? And of course, always another thing, it's always a nice skill to have. You never know when you'd use it. But one of the things to remember, though, is that there are two great sayings about models. One of them is all models are wrong, but some are less wrong than others. And the other one is all models are wrong, but some are useful. So the idea here is the computer is not going to exactly model your antenna the way it's sitting out there, maybe strung between the trees or past your rain gutters or whatever. It's going to give you a pretty good idea of how the antenna works, but it's not perfect. So a little bit of background. The problem of computing the actual behavior of an antenna is basically modeling, given this piece of wire with RF currents running up and down in it, generating magnetic and electric fields, how do those fields actually work? And that's a pretty complicated problem. It's probably too hard really to do in any significant way by doing it by hand, but once you could get enough computing power, you could kind of use the computer to do the modeling to reduce these complicated equations and actually numerically compute the properties of the fields your antenna is generating. It's still a complicated problem, but a computer can handle that. And it took a while until computers were capable of doing the calculations. Probably sometime in the 60s, it became reasonable to ask a computer to do it. So around that time, Lawrence Livermore National Lab, those are the people that build the bombs. There's one lab that designs them and another one that builds them. So Lawrence Livermore developed a code called NEC2. I think NEC stands for National Electromagnetic Code, and 2 is the second version. There's now a NEC4 and NEC5. NEC2 is still widely used. The source code is available. It's written in 1960s or 1970s Fortran. And you can go on the internet, you can actually find the code and review it, compile it, do whatever you want. But a lot of people, the problem with NEC, it was designed, it's written in Fortran, designed for 1970s era computers. So the input was via punch cards and the output was on a line print. And, those are the days when you punched, like columns 7 through 11 was something in 12. So God forbid you got the columns wrong. And of course, on top of that, you have the problem that no one has punch cards. So what do you do? So you can type in the things very carefully, getting spaced, but that's just not done anymore. So you really just need something to kind of do some of that work for you. And so what a lot of people do is they'll write a front end, which gives you some nice graphical, spreadsheet-like way to enter the description of the antenna. And then the program will turn that into the punch card code and feed it to the program. The program does its stuff. The front end now grabs the output and puts it into nice pictures on your screen. So underneath the program I'm going to describe for NEC, which is a freeware front end for NEC, EasyNEC, which has been around for a long time. The ARRL would give you, if you bought, I think the antenna book, you would get a limited version of EasyNEC, which would let you do simple things. EasyNEC itself was a commercial product. The guy who wrote it just decided he was done. He retired, and he released the program. So you can now get EasyNEC, the full-fledged commercial vac, just by going to the website. Just look up EasyNEC, but no support. So I'm going to use. I'm most familiar with this one particular program for NEC, which is free, and so I'll show you that. But EasyNEC works almost the same way. So what is this program going to do? It takes you model the antenna. You say, I got a wire from here to here, and there's a source at this place in the wire. And then it breaks the wire up into small segments. Think of an 80-meter dipole cut into segments about 1.5 feet or 2. And it calculates the currents and the field generated by the current in that segment. And it adds up all the fields and whatever, and then gives you the result of the whole antenna. So the only reason I mention this is because this is, in knowing how this works, is how you describe the antenna to the computer. So I already went over this. Okay, so EasyNet is, you can get, it's EasyNet, you just EasyNet, I can't remember the URL. 4NEC is the one I've been using because I was interested in modeling antennas, but not interested enough to pay $150 or $200. And 4NEC 2 did the same thing. It was free, and it was supported by the guy who wrote it is still supporting it. Essentially, what I'm going to describe what is particular to the program I use, but they're all pretty much the same. So one of the other things, if you want somebody who can take the time, more than the 45 minutes or an hour I've got here, LB Seebeck, who was like the guru of antennas, wrote a long series of articles in QST about antenna modeling, and you can get them on the ARL website. And there are other, the internet is a trove of things. I would stick with Seebeck. Seebeck really knew what he was talking about, and he was he made his living doing that professionally. So, okay, so what does the program need? Well, first of all, you need to basically tell the program somehow how is your antenna laid out? The ends are here and here. They're so high. There may be more than one wire. Think about modeling a Yagi. Just a simple 3-element beam. You've got 3 wires, right? You've got the driven element, the director, reflector. So in general, the program thinks of these as wires, although some of the wires you can actually specify the diameter of the wire. So some of the wires may be tubes, but, and you do it by giving the 3D coordinates of the endpoints of the wire. Usually it's X, Y, Z. Z is the height above ground, and X, Y are 2 arbitrary directions. You can think of north and east, or south and west, or whatever. What I do, because you can do this anyway, you can make your life complicated, you can make it easy. I have a convention that I always take my antenna elements parallel to the y-axis. And if there's multiple, they're spread along the x-axis, and z is the height. So, so you can, once you do this, I mean, if I have my antenna, it's just, think a simple dipole laid across the y-axis, then it's going to broadcast on either direction along the x-axis, but that is, there's no north-south built in, right? That's, you kind of assume. So for the dipole along the y-axis, x could point north or south. So you can kind of convert this arbitrary system into something that's more meaningful, like north, south, or east, northeast, depending on how your antenna is actually laid out in your yard. So 2 things that makes it easy. I put my antenna elements parallel to the y-axis. You can, if you choose, make them parallel to the x-axis. You make them at any angle you want. I also tend to center them on the x-axis, so they're kind of symmetrical that way. It makes it easier to enter the data, and it also makes it easier to understand the output. So I'm going to switch because I thought instead of talking about this, let me actually model some antennas here. So I'm going to go through. I'm going to go through a couple of examples, and then if we have time, I could even accept the challenge from the floor, provided it's not too complicated. But so my apologies to the people online.
It's okay.
So too many mice here. Okay. So here's 4NEC2. Okay, so what I've got here, let me set up. Well, this happens to be an example of an antenna that I actually built. This is an end-fed antenna, 45 feet long, and so this is a 3D picture of the antenna.
Daryl, is it
Sorry?
are we able to get it back up here?
I guess not.
Okay.
Oop,
Now, that's weird. It's still going on the screen. Well, they're not seeing it, of course. We don't have any way, so just look at one of the side models.
So, so you see it, there's a 3D, and then here is an SWR curve, for example, of that antenna. Here's what the impedance of the antenna looks like. This is frequency along one axis. So let's go back and see. So this is how you actually input data. You notice it's a spreadsheet-like thing. So the antenna is described by a number of wires. And so here's a wire. This particular wire it has a tag that just identifies it as what, if I have multiple wires, each one has an individual tag. Segments tells it, take this wire and split it into this many pieces. And then here are the X, Y, and Z coordinates of one end of the wire and the X, Y, Z coordinates of the other end of the wire. And this last column, radius, which is what I would put in if it were a piece of tubing, but it also lets me put in, this is a number 14 wire. And then this is wire number 2, has a lot more segments, and you can see it goes from X equals 0, Y equals 0 to X equals 0, Y is 45. And I also have this little piece, this 5-foot piece. This first one is actually a counterpoise. A lot of these end-fed antennas like to have, even though it doesn't seem like much, 4 or 5 feet of counterpoise hanging off the other end makes the antenna work a lot better. So this is about as simple an antenna as you can do. Notice that the one end of the counterpoise is the same coordinates as the beginning of the long wire. That automatically joins them. And so there are a couple other things. There's a source, what's driving the antenna, and it's in tag 2. That means it's wire number 2 in the first segment. So it's right at the beginning of the wire. And then this is basically a 100 volt, okay, or 100 watt signal. So, and then there's a section here. If you want to do, this program will actually do what optimization, that is, you can set, instead of saying some length is so many feet, you can give it a symbol like A, B, C, and then you can ask the program to adjust that and to optimize like lowest SWR or maximum gain or so but the other thing that's important on this tab is what are the units? The units, the default for units is meters. So if you want, if I had not gone in here and clicked units or in feet, I would have ended up with a very long antenna. And I would not have figured out what was going on. Why is it not resonating where I thought it would? So, so having specified the antenna, this is just a layout where all the pieces are. Then I can go over here. So this is some of the options. Daryl.
I'm trying to figure this out on the fly.
Yeah, well, meanwhile, they can't see what I'm doing.
That's what I'm gonna, okay, well, at least we got that much back.
So I'll do that again.
Okay,
So if I want to capture stuff, I ask it to do a calculate. And I like to do a frequency sweep. So here I've said I want to do a frequency sweep from 6 to 30 megahertz in steps of a tenth of a megahertz. And so I just sort of generate. There you go. Now, mind you, that was 240 times, that was calculated that each one of those points, it had to go through the whole, figure out what the currents are, add them all up. It did that 240 times in that little blink that we took. On the 1970s era computer, we would have had time to go out for lunch.
right.
But you can see this particular antenna seems to have a resonant point around about 9.5, 9.3, and another one here at 19.7. Not particularly useful frequencies, but now what I could do is I could say, what happens if I made the antenna a little longer, a little shorter? What if I change the counterpoint? So I can do all this by just typing in some different numbers. It's a lot easier than actually doing it in the field on wires. Okay, let me show you a more complicated antenna. You can see here I have a lot of antennas I've modeled.
Yeah, you bought quite a few.
I put on my glasses so I can see what I'm doing. Okay, this is an antenna. I actually wrote a paper about this for QEX a couple of years back. The essence of this antenna, this is a dipole that's a little bit short on 40 meters and a little bit long on 20. And by putting a set of traps, that's what these little boxes are, in there, I can actually make the traps work so that it's resonant. The trap makes it resonant on 40 meters and also on 20. And so this antenna is a little bit more complicated to, sorry. So here the antenna is cut up into basically more pieces because I want the piece from the trap out, from the piece from the center to the trap in both directions. So that's 4. And then I put a little very tiny section in the middle where I put the source. So, so this is, you can see, it's a lot easier to see here. There's that's what the antenna looks like. It's this long wire with a trap at either end now. So it's got the source, but it's also got a load. And here, down here on this tab, I've entered what kind of load it is. In this case, it's an LC trap. And here I specified the capacitance and inductance of the trap. And they're the same on both sides. And if I now do a frequency sweep on this, I'll just leave it the same.
The blue line's SWR, what's the red line?
Oh, hang on a second. That's the reflection coefficient. Yeah. So this is what the SWR, and what I did here, now this is, if this is the SWR, assuming a 450 ohm system. And the reason for that is that, oh, hang on. I left this in a weird. It should be 50 ohms. There we go. Oh, the 450 ohm is for the end fed. With the end fed, I feed it through a 9-to-1 balun. So effectively, 450 ohms at the antenna is 50 ohms on the other side of the balun. So, but here, this is this trap antenna, and you can see it does work. There's the SWR at 7, and here it is again at 14. So you can see this very sharp, the resonance it's at in 40 meters is pretty sharp, but the resonance is broader at 20. Now, another thing I can do over here, I can change the display. So this is now the impedance of the antenna versus frequency. The blue trace is the resistance in ohms, and the red trace is the reactance, also in ohms, on this scale. And down here, this is the magnitude of the impedance and the phase angle. Probably a lot more than you really need to know, although I find this one useful to go back and forth. So now the other thing that the program has done, I haven't shown it yet, is it's calculating the fields, the actual field pattern here. So that's what the field looks like. It's pretty much what you expect from a dipole. It's sort of a donut, half a donut lying on its side, kind of bulging slightly. You can see the peak. The peak is kind of, I think the peak actually is mostly straight up. This antenna is not very high off the ground. So it's very good for heating up the clouds or for talking to your neighbor 3 houses down. So there's nothing here that's very surprising in that sense, but what this does confirm, for example, is that the trap values that I calculated do what I more or less want them to do, which is give me 2 resonances, one at 7, one at 14. And even though the thing at 7 is very narrow, it gives me enough bandwidth that my rig will, my auto tuner will deal with it, especially if you stay in the CW part of the band, which is where I happen to operate most of the time. So, this is a, I mean, what you're seeing here is the result of probably a couple hours of work of trimming, of trying various combinations of L and C in the traps to get a decent, 2 decent minima about where I want them. You can calculate the paper I wrote for QEX talked about how to calculate the actual values. And so you start there and then you discover by tweaking them a little bit, you can move these dips around to get a more precise answer. So let me. This is what, this is the kind of thing that this program has actually generated. This is the actual input to the NEC program. You can see it looks like punch card data. It's got numbers in regular columns. Like a lot of these things, if you have any experience from that era, there's something that in the first column that identifies what the rest of the data is about. So for example, these are comments, this GW are wires. And then most of this is the data, the length of the wire and the number of segments and so on. And then here's a source, GS. And then these are the parameters of the trap. So this is what this front end is doing for you. It's taking that data you enter in a simple spreadsheet-like table and turning it into this, which is what the NEC program wants. And there's a corresponding output file, which is much bigger and much messier, which the program then takes and turns it into the nice graphical display. So both 4NEC and EasyNEC both work on with the same underlying engine, the NEC2 engine. NEC4 and NEC5 are available, but you have to pay for them and you need a license from the government. They're considered, if not top secret, they're at least considered vital technology. And so you can't just send the check in for $200 and get the code. You have to kind of pass some kind of background check. And they will do a better job than NEC2. They're more sophisticated algorithms and whatever. But for the purposes that we're doing here for ham radio stuff, this is plenty good enough. So as you can see, these are my antenna modeling files. I've got a whole bunch of, let me see if I can, for a while, I was trying to find modeling a vertical with various top hats and other things. So sorry?
Are those antennas that you actually entered in
That-
inside,
that-
or is there like a library somewhere that people may have, like, so, let's say somebody characterized the buddy pool, for example, is that already out there somewhere?
The programs, both this program and EasyNEC come with a large pile. There's a whole bunch of, all sorts of antennas, really complicated ones. These are all ones I did myself.
Got it. Thank you.
Okay, this is a kind of antenna that deserves to be better known than actually it's called a Moxon. It's the Moxon is basically take a 2-element Yagi and bend the ends, front end, bend the ends of the driven element backwards and bend the ends of the reflector forward. So you now have almost a rectangle with a little gap between them. And it was invented by a guy named Les Moxon, who wrote a book, the RSGB book called I can't remember, something like antennas for every space. If you're seriously into antenna design, you have to own a copy of this book. It's Les Moxon G4, I think XN. But this is a beam he designed. This particular design it behaves like a 2-element Yagi, but has a better front to back ratio. And it has almost the gain of a 3-element. It's something like 5.5 dB. So it's also more compact because instead of having the ends way out, you've bent them in. So the antenna is physically smaller. So it's not. This particular one it's for 2 meters, so it's not very big. But there is a small gap in there, and so you can see here the SWR. This one is a little. This one, wherever I left it, it's a little. It would be a great antenna, probably around 150 megahertz. So one of the things I want to do is to squeeze the dimensions down. But one of the other things you can do, let's look at what the far field pattern is. So that's what the antenna pattern looks like. You can see it's got lots of lobes, but it's got a lobe sticking out here very near the horizontal, which doesn't make much difference on 2 meters, but you could build a 10 meter. I have a 10 meter Moxon that I actually built at a PVC for the arms and then the wires around the out. And with a nice low angle like that, that would be a great DX antenna. It's a little bit too big for me to put up in my yard, but one of these days, now that 10 meters is actually showing some signs of life, I may well put it up in my garage and in the attic of my garage and see what it can do on 10 meters with a real antenna. If you, speaking of 10 meters, if you're interested in DX, 10 meters is opening up now, very often middle to late morning. And it's sneaky because you can very often, there will be 3,000 people on FT8 on 20 meters, and there will only be 15 on 10 meters. So if there's a DX on 10 meters, you're much more likely to find them on 10 or 12 or 15 meters than on 20. So this is a more complex antenna, and I'll just show you. See, it takes a lot. See the description of the wires. There are a lot of wires because you think about just the front. There's a wire which is start at one end, the left end of the driven element, which is here. So you go from here to here, forward, and then you go across, and then you come back. And I actually have the driven element split in two, so in the middle I can put the source. The reflector is, again, just 1, 2, 3 pieces. So that's already 6, 7 pieces of wire. And then I've got little extra pieces. So I sometimes will put in a short segment so that you can place the source exactly where you want it. And so this is again a more complex layout. This is think of this as even more complicated than a 2-element Yagi. A 3-element Yagi would be even simpler. This has got, because of the bends, it's got a lot of pieces, but nevertheless, it lets you can see, you can make up a pretty complicated layout. And then, and by the way, this this diagram is very useful because very often when you first lay it out, you discover you've got something wrong and it will show you, an element going this way when you thought it was going this way. So the picture, and let's see. So, so my general feeling about this kind of thing is that if it's something you're interested in, you can't break anything running the program. You can't fall out of a tree sitting at your desk, right? You don't get strands of copper wire in your fingers. I mean, if ultimately you're going to go out and climb the tree, you don't want to have to do it more than once. And so this is the thing that will get you close enough so that you can now go out and put the actual wires up in the air, however, and then you can look at the results you get from that and compare it to this, and you can kind of see they're not going to match exactly, but they ought to be pretty close. And so what that will let you do, now the program will tell you, well, look, this SWR curve is shifted a little, but I can go in the computer and see what do I have to do to shift the SWR one way or the other. And then you can then go out and do it to the actual antenna, adding wire, cutting wire off, whatever. So this helps you design the antenna to start with and play with the design till you get something that you like. And then you can then come back, go out and build the actual antenna, install it, and then see how the actual antenna compares to the model. And then because the model and the reality aren't going to match exactly, it will be, but they will be close. And therefore, what you do to the model will more or less do the same thing to the antenna. If you make it a little bit longer and the SWR point shifts some way, then you know the same thing is going to happen if you do it to the end outside. So this will, if you're into building antennas, this is really a tool that ought to be in your kind of toolbox. And I am just about out of time.
Yeah, we're getting pretty close.
Yep.
Are you back to your presentation now? Are
I,
you doing any more demo on the screen?
anybody, yeah, before I switch back to the presentation, anybody,
Quick question about the
Yes.
Z-axis is the height above ground.
yes,
Z-axis, so you could actually do that or the Z curve model, and you can kind of see what the ground effect would be on the pattern. That.
yeah, you could just change the height,
And then you could actually see how it's changed, how the ground is actually changing, right?
right?
It's the large pattern.
Yeah, what I didn't show you, there's an option for, you can also do this in free space,
Okay,
okay? But if you can say, I want to use a real ground, and it has a model for how real ground, and you have to, there's a difference between real ground when you're sitting in a swamp and real ground when you're sitting in a desert.
gotcha.
And so you have to look up the parameters for Florida, which I think is damp sand, kind of.
Except where I'm at, I got wet dirt. I got wet dirt out where I'm at.
Thank you, appreciate it.
Yes,
Does the program have any parameters that would allow it to take into account the proximity to large objects or structures like a roof?
yes. I've talked about writing, modeling antennas as wires. There are, because if you think about the people who are really using this, they're not hams, they're designing antennas to go on airplanes or radar antenna or whatever. And so the program can actually model something more complicated than a linear wire. You can actually, a sheet of something, you model a helix. So you could, for example, have a wire antenna and then just have a sheet of something nearby to model the roof. You can make this, you can add all that kind of stuff.
That was actually close to what I was gonna ask. The EOC down here in Charlotte, it's got about a 60-foot roof. It's about 140 foot square. And I was thinking about mounting a end-fed half-wave across the top of it. And was trying to figure out just how you would model that, because the roof is solid steel, or it's not just beams, but it's steel under concrete, strangely enough. There's an entire grounding wire that goes around the edge of it for like, for lightning strike and EMP kind of stuff. So I was trying to figure out how you would model an elevated roof, because mostly the thing that AMS can add to the EOC world in HF is that there's not a lot of EOCs that even have HF anymore.
Yeah,
Most
well,
of the HF around is actually ambient. So that's kind of most everything else we're backing up some public safety, threat. But now we're almost in a unique position. But I couldn't figure out exactly how to model that. Have you ever tried to model something like that?
yeah, I would just assume I mean, your wire is going to be over the roof.
Yeah, it's
So
like maybe 10 or 12 feet. Like if you laid a that halfway from the ground, you get mostly NDIS and a little bit of DX. If you took it up to an 80 meter up 130 feet, you get mostly DX and a little bit of NDIS, because it's pretty invariant in that half waves are, as opposed to random wires. But I couldn't figure out what you would do. 60 feet's right in the middle of that. And I couldn't figure out if it would act more like it was close to the ground or in this, or it would act more like it was,
if you've got a solid steel roof under your antenna,
yeah, it'd be
that's
about-
ground.
You'd swing it across the roof, parallel to the roof at about, they have all kinds of microwave shots up there, and like lots of sturdy, there's a foot plus thick, 2 or 3 foot, perimeter goes around the top out of concrete, and then they have lots and lots of 3 and 4 inch posts sticking up above that. You could use to mount an end fed halfway from one side of the roof to the other.
Yeah. I would model that as forget the real earth underneath you. Your ground is the roof.
Yeah,
And so you may only be 10 or 12 feet above the roof, and you can actually tell it's perfect ground,
yeah,
right? I mean, there are people, I never met one, but there are people who will actually lay chicken wire
right.
on their, and then grow a lawn on top of that. And that, especially if you're using verticals, that makes a great ground. But, that's another case in which you would actually just say, forget what the dirt is underneath this chicken wire, this metal roof, whatever, that's the real ground. And it's perfect ground.
All right. Well, it looks like we are running up to the top of the hour. So at this time, we're going to end the stream. And Dave, thank you very much. Excellent presentation. We will now end the YouTube stream, and we will commence with that at